Heyo, how are we doing, everybody? I think called it. Had my audio on the background. I could hear it. Who's all in the chat? Let's wake up Mewbot here. If you're here, say hey in the chat. We're re-waking up Mewbot. He'll destroy the world as he always does. There you go. He's back waking up in the chat. Let's go get the activity and practice some code. Who all is here? Just sent out the announcement to everybody. We've got activity coming up right here. Due on Friday. So let's get taking a look at this. Some simple linear regression. Here we are over to the main screen. We've got the file right here and the practice file. And let's open up the practice file and take a look. We've got a data file. Oh, we're going to do some Xbox stuff. Sounds awesome to me. We were doing some regression to start out. And let's start here on the first thing. So there are two files that we had. One was a data file, I believe, on Xbox auctions. And the other is the RMD file, which is an R Markdown file, which you currently see. Bunch of things right here, just the author and all that good stuff. We won't be knitting it, so not too important. Xbox auctions, love it. And we're going to start by loading this in, and it's not giving us the code. So all we're doing right here to load it in is we need to have this in our working directory. If you run into a problem where you try to load in this file, which is a DAT file, and it doesn't load, it's probably not in your working directory, or your RMD might not be in your working directory. Let's go ahead and clear everything out right here so we can have a little bit more of a clean slate so we don't have a bunch of things we're not using. And your R might look a little bit more like this. We don't have any plots loaded up, nothing's been run, and we don't have anything in the brain of R. Remember, this is the brain right here. It's what R currently knows, and R is Jon Snow right now. It knows nothing. And let's take a look. This is going to read a CSV file. Reading it would just read it. We don't want to just read this file, though, which would just do this. We want to take what this is and store it into the object Xbox. So now we have some Xbox auctions. Gosh, this is old if these are original Xboxes. On eBay. 149 auctions on eBay for the Xbox 360 game console. We're 2 generations beyond that. The variable of interest is price, making it the Y variable. So you can see here a bunch of X variables. And we have here Y variables. And we want price is the Y. $311 for a 360. Cool. And let's take a look. Make a scatter plot to examine the relationship between price and bids. So we might think that there's a positive relationship, like when there's more bids, like 2 Xboxes that differ by 1 in their bids would be expected to provide this much in their price, where the Xbox that has more bids is expected to have a higher price. It's all expected, never say will, be careful. Now, one way to make a scatter plot is to go here to plot and put in your y tilde x comma data equals. So we're going to go here to price is the Y variable of interest. Right there's the formula. Tilde, bids, comma, data equals, and the name of our data set is Xbox. Use the autocomplete when you can. And we get the following. And there's a lot of outliers. QQ, straight enough. No outliers. If a 201 student hops in the chat, I will throw 500 points right now. Who's ever here 100 points? Mewbot, you awake? Yep, he did the thing with the points. And so right here, is there a relationship? There's problems here, though. This is ridiculous. Someone's paying $500. That better be like a Halo First Edition Xbox 360. No idea what's going on at that point, but you can see right here about 335 bids and close to $500. We can actually view that one pretty quickly. It has the highest price. So there it is right here. It is row 131. And you can always click your data, just look at it. And if you want to quickly find that, we can find it. There's other ways with code. You could go to which.max of the Xbox data frame and go to the price of it. And that is the row we just saw. And I oftentimes call this position right here. So we could find the position. And then we could go to the Xbox and just return that row. So we're doing the same thing as we did by just clicking over here and doing this. You can get it with code, or you can, especially with smaller data sets, do it by visually examining it. 5 days it lasts, whatever the duration means. There were 32 bids. You can see right there about 32 bids. The price 501, and the opening bid was 150, and the bid rate for how fast the bids were, and the bid time right there. All that good info. So is it a straight line goes through it? Yes, the bigger issue looks to be outliers. Straight enough, maybe. Fint the model for this, okay? So actually what we're going to do is we're going to take, so that's the end of one, that is how to do some simple plots of data right here. So it's just a simple plot y by x. Now we want to fit a model to it. So let's talk about how to fit a regression model to this. This formula right here, which is the y tilde x comma data equals, you can see it right here, is going to be very important. We're literally just going to copy this code. And we're going to bring it down here to this problem where we're going to use a linear model. Now, we haven't stored this object, but this actually creates a linear model with an intercept and a slope coefficient. Here is your intercept, b0, and here's your slope, b1. But this just ran it. We want to actually store this object. Now, the reason we save into object m is because we call m model. You start making a bunch of these, you could call it m.1 or 2, or you could call it model.1. Just some naming conventions. It doesn't matter what you call it. Rock, what do you think?
It doesn't matter!
You can just call it whatever you want, and you'll just be storing into that object. This creates a list, which is like a folder of things to look through. So if you ever want to take a look, you could look at the residuals. Here's the residuals for our model, which is how much we miss by. We could go right here also and take a look at the fitted values, which are the predicted values. So there's the predicted values for the model. So this is giving us all the predictions the model would make, but we're not actually looking at this model right now. I don't love this way of doing it, but you could do the following. You could go right here and use the AB line, or I call it AB line, to add a line. It stands for AB line. And you would want to replot your data. Copy paste is your best friend. I can't state that enough. Ask coders if they copy paste, they'll say yes. What we're going to do right here is we're going to append onto this code. To append code, you use the semicolon to run another line of code on a current line of code. And the AB line will take this model right here and draw it on here. Now this looks a little We can add a second argument for col for color, and don't use the autocompletes right there, and type red. But if you really prefer, you can do a hashtag for hexadecimal coding and do FF8200 and get some Rocky Top right there. If it's not clear enough to see that that's Rocky Top, let's increase the line width, LWD, and change it to 3, and now we see the line of prediction right here. This is not required though, and I kind of say meh to this because we could visualize the model with this. This is what Dr. Petrie wrote, so we can get a visualization of the model right here. Aiden, good to see you here. You can't hear me? I checked my audio. I think we're good. I think we're good. I'm going to actually listen to myself on the stream now. Ready? No. Change it to 3 right here. Aiden, good to see you here. We do have audio. Good. I was so worried. There. I was like, oh no. I actually have done that before. I've got a mute button over here. Right, you didn't hear me there because I was muted. But I do have a mute button. So if I ever hit this, I am muted. So it's really good if I'm like sneeze or something like that. I didn't even mute myself. So yeah. No worries right there, Hayden. Great work. And so we've got the visualization of the model. But I like right here that we ask you to do an additional thing, because there's an additional model to look at that people forget a lot of times. And we actually write the code for you right here, and I'll explain what the code does. Let's append this on, and let's do col. Here, we'll just, I'll do it this way. It's a lot of code to just talk about a concept right here. And this concept is the what model. What is the flatline model? Plot new. Yes. You must append it. Here, I'm going to drop this in the chat right here for you. Thank you right here for being here. I'm going to drop this in the chat for you. Check your code with it. There's that complicated code I just wrote. Check your code with it. And I'm going to drop the other one, the first one I wrote in the chat, so you can use these codes right here. I'm doing hexadecimal color coding for colors. If you don't want to do the FF, all this stuff right here, the hashtag, you can just write orange. You won't get UT orange then. You'll get a very close to UT orange, but not quite. That's hexadecimal color coding, which is we don't have to do. But what is this blue line model? What's the deal with this blue line model? Yeah, copy pasted to them. Tell them jump in here. Thank you so much, Max, right there. Thank you everyone for answering all the questions on Discord. I'll hop on. As you guys and gals know, I teach from like 8 to 5 a lot of days with office hours, and I'll go to the Discord and people have been answering each other's questions. So yeah, drop that code right there in the Discord. So what is that blue model right there? Can I actually add it? I think I can add it. Let me try this. Add text to plot in R. I always forget the code for this. Here we go. Is it just the text, the XY? So let's go here to text. And then we can go here to X, Y. Well, that's not. I just want me to write the thing. Okay, wait. Okay, that's it right there. Okay. So text, let's go right here to 60, comma, 80, comma, naive. Boom. Call, no. Equals blue. Look at that. Look at that. Awesome. And then let's go here and do the next, and let's do text. It's just that simple. It's just text. And then we'll raise this up to 250 or so. So the Y coordinate needs to go right here, and it needs to be orange. And then we need to go here to predicted. There we go. And that's our model. So kind of making a decent visualization here to show what's going on is that we have the naive model, which is the mean of Y. And then it might look a little better down here because the text's a little bit bigger to see. But does this make sense right here, Max, that the naive model is the mean of Y? So look at how we're finding it mathematically. It's a lot of code, but that model right there is just the mean of price, and price is the Y variable. So it's adding a line. That's what AB line does. We've got a lot of arguments on it. But we're just making a line right here that has a mean on the Y variable. It's the mean of the Y variable is a line right here on the plot. We're adding it to the plot. So you have to make sure you make your plot and then append code to it. Not my favorite way of doing stuff because there's a really cool way of doing it. And do I have that package still up? I want to show one really cool thing right here. And do I have it up? It looks like, well, I gotta remember the name of the function. Let me go to my functions. gggraph extreme extra. And let me look right here. Functions gg. Oh, I got to take a look at this later. I found this thing right here, gg predict, I think it is. And yeah. Here's what I found earlier today. And take a look at what this does. Oh, and then we need to do interactive equals true. So this creates an interactive plot right here where you can actually see the equation of your line. And I don't like, why is it off the screen a little bit right there? That's weird. This creates, really? Oh, there we go. So this creates an interactive line, don't like that, where we can actually see the equation right here when we hover over it. And we can actually look at the points themselves and see that that's 0.8. And remember 0.131? So I think this is a really cool code that I found online. I had to download it from somebody's GitHub, but I wonder what they do. But they made a pretty neat thing inside of R right here. So this is all being done inside of R, and you could literally hover over a point and tell what it is. So you get all these interactive plots. You can even move it around and stuff. I think that's what that does. I was messing with it earlier. But really cool right here, and really great way to do the visualizations compared to some of the easier ways right here where we're viewing it with just this graphic, or we're also viewing the same sort of visualization. That was ones I was making earlier with it. Here's a visualization here of it, and here's a visualization here. So you can see it's the same sort of thing, but we did include in this the naive model. And it'd be a little more work to get the naive in the other one, but the naive model is an important concept to know. That is the mean of Y given some X. For the remainder of the class, the quickest way to get your models is to do what? So Max and everyone, good question right here. For the remainder of class, what is the quickest way to get your models? Once you build a regression model, look on line 50 something, what is the quickest way to just get a regression model rather than going to plot and all these other things? The quickest way to get your regression model is going to be to do what? To draw it out, to visualize it, to see what's going on. Right there. This is going to be a much easier way by going to visualize and go to visualize model, and it'll just visualize your model for you. Which, if you look, this is very similar to what we have right here. You might even think it looks a little bit better. This is an interactive one, which is way cooler, though, which can't be knitted into Word, but you could always take a picture of it. There's the download of the picture of it if you want. So I really like what this guy did with these plots. Really neat how you have all the interactivity on them. That's it for question 2. We've gone through and we've talked about the naive model, and the naive model is the base jumping off point for which we calculate the sums of the squared error. Next, for number 3, we need to talk about some of these coefficients right here. So we need to find the sums of the squared error of the model. Now let's do the long way of finding this first. When we do the sum of the squared error of the regression model, that is how much our model misses by. So our model has an error. This is error in the residuals. The sums of the squared error of the regression model is how far we miss by. Like this point is missed by this much. This point is missed by this much. This point is missed by this much. So we would need to find how much the residuals miss by. So let's go here and find our residuals. Here's the residuals. And you could see like 0.131, remember that point we were talking about earlier? 0.131 has a residual of 347. What does that mean for 0.131? 0.131 is what? 0.131 is what? So if you think about 0.131, if its residual is 347, that means 0.131, and take a look at it visually, is 347. What? There's 0.131, and its value of its residual is 347.12. That means this value right here, this value of its price, is 347.12 above the predicted. Good stat tool 1 stuff right there. So we know 501.77. Watch this. We could actually get 501. Let's do it in R. Why am I not doing R? 501.77 minus 347.1212608, and that is the value of it right here. Its value is 154. Its predicted value. Yes, exactly. Great job right there. Great job, Max. That's how much higher it is because it's a positive residual, and its value would be this. We could also check that by going here and going to Xbox and looking at the prices. And guess what? At 131, which is right here, there it is. It's 507, but let's go to the predicteds. You can actually look at its predicteds. That's what I think the prediction should be. And you can actually make predictions from your model by doing the following and look at 131. Here's the value. And let's double check by running this. And is that the same value? It is, because we were able to tell it's like that much more above it. So we just subtract off to get the predicted value. So the residual was how much more above it is. So the value it is at 501 is that far above the predicted. So I found the predicted by subtracting, and then we confirmed the predicted by looking at the value of what it was predicted to be by running the predicted code. So we are very interested in the residuals though. Well, residuals are errors. So what are we going to do to our residuals? SSE stands for the sum of the squared residuals. So when we have the sum of the squared residuals, we simply take the residuals and square them. And by squaring the residuals, we get squared residuals. And this is the sum of the squared residuals from the model. And that is how much error we have. That is like taking all these errors right here from down to here and squaring it and adding it up. And we do this because could you make your own residuals function? Then if you did, you could. Yeah, great answer right there. Yep. You could make your own residual function, but we do have that. We do have our own residual function in here, so we can get it pretty quickly, but you could if you want. And so here is the sum of the squared residuals, but guess what? It's easier just doing ANOVA. And where do you notice this is at? Very important to see this. The sum of the squared errors on the residuals is right there. Very important to see this. That is the error in your model. This is bad. This is good. This is the bad. Your model did a bad job, did not explain this. Because remember, this is the residuals, which we don't want residuals. It's how much we miss by, squared, so they're all positive, and then added together. So we have the sum of the squared residuals, which is the error the regression model makes, because that's what a residual is. And so we don't want this number to be big. We want our model to explain things, i.e. reduce the error. And what are we talking about here? Reducing the error from what? Well, there's a second model we talked about just a second ago, known as the Naïve model. The Naïve model is the mean of y. So you could do the same thing where you take all of the points in your model. So we need to take Xbox, this is the long way of doing it, and take price and minus the mean right here. This is the difference right here. Like how far is this point away from the mean of price? because we would take a point, find out how far it away is from the mean of price. So we go to the mean of Xbox $price right here. I have a hashtag apparently. And then we take this, that's how far they are away. And now we're going to take this and we're going to square it. And that gives us squared errors. And then we sum it and we get the following. That looks weird. Something's odd. I did something wrong. Oh, I put the square in the wrong spot. Dun, dun, dun. Wait. Negative. No. There we go. One thing off on QTP error. Make sure we put this in the chat earlier. Let me copy it again. Try running this code right here, Avery. Yeah, make sure appending it right there. Great job right there, Max and Avery helping each other out. Make sure to append that. It's easy to make errors in code. Apparently, I didn't have my parentheses in the right spot. So I was like, that doesn't look right. So this right here, what you're seeing on the screen code-wise, is the error from the naive model. This point right here has no error from the naive model. From the predicted, it actually has a bigger error. But the naive model will do worse if we do have a slope to our line. The naive model is a base jumping off point, and this is the original error we have. This is the error our model has. Here it is right here. This is the error our model has. So how much have we reduced the error by? Nice job, Avery, right there. Some 50 points. How much have we reduced this error by? How could we figure out going from the naive to our model, there has been a reduction of what? Just tell me mathematically, if this is the error that exists from the naive, I've coded out how to find the error from the naive. So I found out the error from the blue line. That's what this finds. The error from the blue line is mathematically this. The error from my residuals is mathematically this. How could I look at the reduction? Just tell me what to do mathematically to find the reduction. How could I mathematically find the reduction right here? How could I find out mathematically what's going on between these and find out how much better I'm doing? Mathematically, what could I do to find the reduction? Exactly, just to see the difference right here. And guess what we get? And you may remember that number from earlier. That number is the good number right here, which is how much we've reduced. So how could you find out this first number right here? I just want you to think about the relationship these numbers have. How could you get the 597,000? What would you do to what your model explains and does not explain to find out the total variation that exists from what your model explains and what your model does not explain from an ANOVA? This is what your model explains. This is what it does not explain from the total variation that exists. So how could you find the total variation that exists from the ANOVA? So this is what your model explains. This is what your model does not explain because it's residuals. It's the leftover unexplained variation. So from the explained to the unexplained, how could we get the total variation that exists? Just think mathematically. Exactly. That's Max. You got it, man. You're totally right. You just add them together because either you explain things or you don't explain things, and that tells you how much there was. Because you have this like pizza, and you'll either eat the pizza or not eat the pizza. So you can find out how much pizza there was by looking at how much was eaten and not eaten. That'll tell you the total amount of pizza there was. I just want pizza. Maybe we'll make pizza. I don't know. It's a weekday. Got to be good on the weekdays. Got to work out. Be good on the weekdays. Eat pizza on the weekends. But one important thing we can find right here, what is Brian finding by looking at the variation he explains out of the total variation that exists, which is just the sum of all from the naive. I'm looking at how much I explain out of the total. I have just mathematically calculated what value. By looking at the amount of variation I explain out of the total, which would be the sum of these two, Brian just calculated what value. By looking at the amount of variation I explained right here out of the total variation there was, remember, it would be the sum of both these values. How much variation I explained out of the total variation, like blank percent of the variation in the y variable is explained by my model, or the x variable in my model. I have just calculated the value of what right here. What value did I just calculate? You can see the math on the screen, and you can confirm the answer down below. That confirms we just calculated what, mathematically speaking, by looking at the total percent of variation explained in y by the x variables. The percent of variation in y explained by the x variables right here is what? R squared, max, you're on fire, man. Another 100 points right there. Keep it up. That's R squared because it's just how much variation do we account for out of the total variation that exists. And that's what R squared is. Like, it gets us, knowing the bids on an Xbox gets us 10% to understanding all the variation in the price. Is that, it is statistically significant, very statistically significant. Is it practically significant? Well, we usually miss predicting the price of an Xbox by about $60. Big of a miss there. We did the reduction. The reduction in the SSE is what the model accounts for, which is right here. And this is what we did not explain right there. Now run. Okay, here we'll put another pause. Talking about some regression. Let's check out, my gosh. Ask those questions. We're doing great right here. Keep asking questions. Thank you, Max and Avery, for being here. So now we're going to look at what is called the possible regressions. And this is showing us what we would get by random chance right here. So when we run possible regression, it shows us what is likely by random chance. A regression line that is likely by random chance will have a slope very close to what? Look at these. These were created by random chance, and a lot of their slopes are very close to this. A regression that is likely by random chance would have a slope that is very small and very close to this value in here. So a very likely by random chance regression would have a slope a lot closer to what? And thus it would not reduce the SSE because it would be very close to the naive model. Remember how the naive model looks. Here's the naive model. And then here's what we're getting. Oh my gosh. Here's what we're getting right here. These are the ones likely by random chance. Closer to 0 exactly. And our slope actually looks not like ones by random chance, and we see a large reduction in the SSE. By random chance, we'd expect small reductions in the SSE because the model would be closer to the naive, which is not going to do much explaining. This is just seeing what is likely by random permutations of the data, and it's unlikely that we would see a relationship right here with the y and the x by random chance, where we'd get this large or larger of a reduction, telling us we estimate the p-value to be about 0. If you look, it is very small. This number right here, I think it might not show it. That is 0.1234627. That's that number right there. Pretty small p-value, very unlikely by random chance. So when we do this right here, I want to point something out, though, and this is key for your assignment. When you look at the slope and you want to know the statistical significance of the slope, knowing the statistical significance of the model is the slope, and this is the statistical significance of the slope. But how is this obtained? This p-value right here is obtained from the t-statistic. What is a bad t-statistic to get? A bad t-statistic for non-significance would be 0. Is it bad? It would just not be significant. Because think of the only way to get a t-statistic equal to 0, and I'll show you the formula for how to get the t. It's the estimate divided by the standard error. Probably the best thing I can do is just copy this and then show you right here that the formula for the t is as follows. Take any of these estimates and divide by the standard error, and you get the t. So how would we obtain, just think theoretically right here, how would we obtain a t equal to 0? In what instances would we get for the p-value or the t-statistic of the slope a t equal to 0? In what instances would that occur? When would we get a t-statistic of 0 for the t-value of the slope, which is like a standardized metric to look at the slope? When would we see a t-value equal to 0? So it's just x divided by y. And x divided by y equals t. So mathematically, a slope of 0, that's exactly it. And that's the naive model. And then if the slope was equal to 0, if this was equal to if this was a t, if that was 0, this would be 0. And then the p-value would be the least significant possible because that's the naive model. And the p-value would now be 1. So the t-statistic, if it's positive or negative, would just indicate the slope of the line. So because the t-statistic is positive, it's the same thing as the negative. That's why we only care about greater than the absolute value of the t-statistic. It doesn't matter. Rob, what do you think?
It doesn't matter.
If the slope is positive or negative for significance, it just indicates direction of the relationship. But we see right here the slope is very significant. You might say, why does the intercept not matter? The intercept is not an XY relationship. It's just a point at which the line hits right over here. So we care more about, is there an XY relationship, which would be indicated by the slope of the line? Other things to mention right here, which are in your assignment. The standard error is your uncertainty. If your standard error were to go down, what would happen to the t-statistic? Like, let's say I change this standard error right here to something like, I don't know, like 0.04. Then the t-statistic would do what? That's less uncertainty. Just remember, standard error is uncertainty. That's a good way to interpret it. It's my uncertainty in the estimate of the coefficient of the slope. It tells me about how much I might be off by. So now the t-statistic will do what? If we have less uncertainty in the estimate, the t-statistic will be water. By having less uncertainty, we're just saying hypothetically, if the standard error, which is uncertainty, were to be smaller, then the t-statistic must be thiser. So by the standard error getting smaller, it's just, we're pretending hypothetically it got smaller, there was less uncertainty, the t-statistic mathematically would be water. It would be, and take a look, it got 10 times smaller, so the t-statistic is 10 times bigger. And if the t-statistic is bigger, the p-value is smaller. So you do not want uncertainty. Uncertainty is bad. But here's what uncertainty can be used for. Check this out. I can tell you that a 95% is the standard error computed from a 90. It's going to be used here for a second. It's kind of like standard deviations. Max, I want you to think about this real quick. I can tell you that a 95% confidence interval for the intercept, I could probably do this one down here. I'm going to tell you a 95% confidence interval for the slope, which I'll show you how to find right here, is probably about 1 to 2.6. So I'm estimating 95% confidence that the probably about 0.95 to 2.6. So I'm going to put up here for my guess. How am I finding this for 95% confidence interval? How did Brian find that? And the answer lies within the 68, 95, 99.7 rule. So how is Brian estimating a 95% confidence interval, and what did he do to his amount of uncertainty? I'm trying to do it in my head, so I think I got close. I'm going to go a little lower. Haven't ran it yet, so I can still change it. That's 8.5. That's good on that one. Yeah, we'll do that. Do you see what I'm doing? If you see it, you see it. Max, that's worth... I'm pressing every button. Max, you saw it. You saw it. It's two uncertainties, and the code is confident. And I was kind of close. Look at the answers. I was within a hundredth of the answer. 9.3, 9.92, 0.93. 2.61, 2.61 right there.
Wow.
I was able to get, by looking at it, 95% confidence intervals within hundredths. And it is small numbers anyways, though. And I was going to do the intercept, but we care more about the slope. Now, what's very important about this interval? I'm telling you, and this is big hints for your assignment, I'm telling you I think the slope is somewhere between 0.9 and 2.6. So it's probably somewhere between 0.9 and 2.6. I don't think the slope is what, though? I don't think the slope is what? So I don't think the slope is this, Max. I really don't think the slope is this value, because I think it's somewhere between like 0.9 to 2.6, and I think it is statistically significant. Here's the p-value. But what value is not contained in this interval right here, which would be a not significant slope, which is one of these possible slopes? I don't think it's not... Oh, I got top chat on, no wonder. Live chat. Max already did it right there. And the big thing, Max, you got it, man. The big number right there is 0. We don't want to see 0 because 0 is the what model. Another 100 points, Max. Tell me about that 0 model where it basically is not as good. The 0 slope is the what model, which we don't want our model to be the same as. We don't want to say our model could be the same as this model, which is the jumping off point. We don't want our model to be just as good as that right here. We want our model to be better than it. And it looks like we have good evidence our model is better than it, because this model has a slope of 0. It would be the naive model, exactly, which is the starting off point, and we don't think our model is the same as the naive model, and it concludes with this, which is statistically significant evidence. If this p-value was high, which it's not, 0 would be included. I don't think I have any of those models up right now. Here, I'll make one really quick. We actually did it at the end of class for 201. Here is a model that has a slope of 0 or could have a slope of 0. And if you run the confint on it, running confint on this model, look at this interval. This interval for the estimate of what the slope might be contains 0. And look at it. It's a lot flatter of a line. And we do not have a statistically significant relationship with the slope, which is the x. And then we see here that the true slope could be 0. While we're here, let's talk about that last bit of the output. It might be in the assignment, but let's just mention it. So in the summary, you should know everything. We cover most everything in this portion. And let's visualize it again. Do we talk about runs? Oh, good. We'll be doing that. Okay, we'll wait a moment on those. Okay. All right, let's do the next question. I don't want to do it yet if it's in the assignment. Okay, we did 4. Let's hop down here to number 5. Let's do it. Good practice. Really good practice. Number 5, a regression predicting price from a completely unrelated variable always gives some reduction, yada, yada. The answer, whether the reduction is large enough to be convinced, does a better job predicting price unrelated. The regression model using bids is large. Quote the p-value from the ANOVA table and state where the regression is statistically significant. Easy one right here. Okay. So remember, and let's take a look. We're going to put a chunk in right here so we can do it. We have our model saved. Oh, I'm going to rerun all chunks above because I made some changes. And let's bring our model back. And I want you to notice something. This p-value in the ANOVA right here is this p-value here. And it also runs the p-value for the ANOVA down here. So the model is statistically significant because the slope of the line is statistically significant, but it also runs this down here. Look at the F statistic right here, has a value of 16.985. That must have rounded up. Maybe rounds down here. Jump, you already being weird today. And it tells you the degrees of freedom, which we don't need to talk about that kind of stuff. The F statistic is going to be the observed variation we see compared to what we would expected being explained via random chance. So we saw a reduction, I should say. We observe a reduction of 17 times more than we would have expected via random chance, given there's no relationship between these variables. You want a larger F statistic if you want to see that there's a relationship. Both the F and the T, the F can only be positive numbers because it is a ratio. That the T can be negative because it does include whether the slope is positive or negative. Interestingly enough, 14.121 squared is going to be 16.98. The F squared, or the T squared, is the F. Random factoid right there. I just thought that was so cool. And I don't know why. I don't know. Better statisticians than me will know why, but I just always think that's so cool that you can actually get the F statistic from a simple linear regression. Fun stuff as Brian's brain just goes out. So this is very statistically significant. We see it in the ANOVA right here, which is the overall model, and we see the overall model report down here also, so you don't have to run the ANOVA unless you want to look at where the sums of squares are going. And then we also see right here the multiple R squared, and I do want to mention these values right here, this value right here, and I'll mathematically show it. Let's draw the ANOVA table. I don't love these questions if we ever put them on the test. Not a big fan of this type of question on the test. It's just more math rigor. So this value right here is going to be how many variables are in your model. And so we see just the one X variable. These are how much are used to estimate the residuals. And we don't have the intercept, so there are 149 observations. This is the explained variation by your model. This is the unexplained. And then this is the average amount per. So if you take these numbers, you'd actually need to do divide by 1 here and divide by 147 here. You'll get the mean, which is the average amount you are explaining. So that's just dividing by the two numbers. So if you divide 61,000 by 1, you get 61,000. If you divide 535,000 by 475, you get 3,643. Now the F is a ratio. A lot of times they call it an F ratio in output, which is just those two numbers divided. And then the relationship F has with P is the same with T, where that larger values of F indicate a smaller value of P. And we did see this earlier with the possible regression showing what F distributions look like, because it actually simulates an F distribution over here. And you can see right here a simulated F distribution via permutations. And you can see it starts at 0 and goes up. No, maybe not quite an F, but still similar. I'm going to take that back right there. Don't listen to me right there. But the F distribution does start at 0, and we can look at the ratio, so that is not quite the F because the F value is 17. And so we can get that from the ANOVA right here. Don't love those calculations, but they're useful if you're a statistician. We want to interpret stuff. So let's interpret stuff right here. Very important to be able to interpret all of these. So let's interpret each one of these and make sure we know how to read them. Probably one of the most important things for your assignment is being able, or your homeworks and your assignments, is being able to interpret these values. We're going to go in here and put in a chunk and run this. Summary. Oh, we'll get the do try catch error. Okay, so we have the intercept. The intercept value is this right here. So this is the intercept value, but we would say when an Xbox, and we are in the word portion, I'll show you a trick. If you didn't know this, you can click right here and you can actually see what it looks like when you mark it down. So a markdown file can be knitted to a Word document, as we all know. And this takes a moment to load, but it's actually showing you what it's going to look like when it's knitted. So neat once it loads in and we go down here to where we were at. You can use the quick way of doing it. About right here. Here we go. There it is. There's what the code's going to look like. Okay. Got the intercept. When, that's what those stars do on the outside of it. When there are 0 bids on the Xbox, when X is equal to 0 on an Xbox, we would expect price to be this on average. So we go among Xboxes that have 0 bids, we would expect, but this, let's just add in, this is illogical. As if an Xbox, it's proper, has 0 bids, it will have not sold for a price. If price was negative, it would also be illogical. Slope right here. Now this is the one where people lose points. I can't make this any more clear. This is where people lose points. Do not interpret this as for each increase in 1 unit increase in bids. Don't do that. You will lose points. Don't just quote the numbers. 2 Xboxes that differ in their bids. So whatever we're talking about, 2 blanks that differ in their X by 1 are expected to differ in their price by this, where the Xbox with more bids is expected to sell for more. That's key interpretation right there. 2 blanks that differ in their blank by 1 are expected to differ in their blank where the higher blank or the lower blank is expected to. Be careful because it could be positive or negative. So be very careful, practice this. But 2 blanks that differ in their X by 1 unit are expected to differ in their Y by B1 units, where the one with the higher or lower is expected to have the higher or lower. Just give it context and then read it to yourself and see if it makes sense. You know, if we have 2 Xboxes and they differ in their bids by 1, I'd expect them to differ in their price by about $1.47, $1.47.6, whatever we got right there. Where the Xbox that has more bids is probably going to be the one selling for more. Don't put will in there. You'll lose points if you put will because we don't know this. This is just what the model expects or predicts. The standard error of the slope is actually our measure of uncertainty. So we estimated the slope to be 1.7690, but we could be off in this estimate by about. Now we don't know we're off by this much, but this is like I don't know, it's like I'll arrive at 5, but I might be off by about 10 minutes. I'm not saying I will be off by 10 minutes. It's like, I don't know, you arrive at 5:11, they're like, you said you'd arrive within 10 minutes. I didn't say within 10 minutes. I said, I don't know, I'll arrive at 5 and might be off by about 10 minutes. So maybe the slope's about 1.7690, but I don't know, we could be off by about this amount. That's about how much we could be off. It's an uncertainty in your estimate. You don't want uncertainty though. You want the uncertainty to be small and make that t-ratio big and make the p-value small. So you do not want a lot of uncertainty in your estimate of what the value of the slope. Intercept, no one cares about your intercept. The RMSE, very important one right here. There we go. So does that mean that technically the standard error is like 68% confidence for the finding? Yeah, it actually is. If you think about it, we would see, you could use it to do a 68% confidence interval. Watch this, you ready? 68% confidence interval, the lower bound on a 68% confidence interval. If you were to take this right here, that's the lower bound on a 68. Max, you're on fire today, man. I'm throwing another 100 points right here. You could just do one of these, and you would go here and go confident, and M and do level equals 0.68. And guess what we get? Here's the lower bound and here's the upper bound. And it's doing more precise calculations than we usually carry decimals. But by doing plus or minus 1 standard error, then you're saying, well, I think that I'm about 68% confident the slope is between this and this. Max, that's that 201 knowledge right there carrying over to be like, well, you could just use it to make 68% confidence then. Right now, I'm going out how many standard errors right here. So if I run this code right here, I'm going out how many standard errors. About how many standard errors I'm going up and down if I do this right here. It's just like if I make a 99.7% confidence roll, then this is the 68, 95. So I'm going out 3. So if you were to check this here mathematically, you could times this by 3. You see the upper bound is right there. Very close to. Remember, it is carrying more decimals in the background than we would be carrying. It's doing a much more precise. Yep, so there's the 99.7. Now, people often get confused because they say, wait, this isn't 68, but remember, it's the middle 68. So if you were to subtract these numbers, you would see 68% contained in there. So it's the middle 68, like we draw on the normal curve when we do the middle 68. So it would go down to 16% and 84. So those are the percentiles on the normal curve. So really good stuff right there. Great knowledge on this is your level of uncertainty, which could be then used to make a confidence interval. So if I tell you I'm going to arrive at 5 plus or minus 10 minutes, then maybe I'll arrive at like 5:15. But most of the time, 68% of the time, I'd arrive between 4:50 and 5:10. Max, that's top tier knowledge. That's what we want to see. RMSE is a little bit easier. RMSE is the typical miss the model makes. It's standard error again. RMSE stands for root mean squared error. And every time I ask this, I always say, which of these cancel? Take a moment here and just think mathematically, which of these cancel when you do root mean squared error? And I'll tell you some stuff we were just doing 201 because it's review of 201 stuff. When you think what cancels with root mean squared error, the two things that are going to cancel right here. Oh, not going to let me underline with the quick buttons. This is what cancels right here. So you're left with mean error. So this is the typical miss the model makes when predicting price of an Xbox is about 60. You can say it is this. I like to say about. It's about this. It's the typical miss we make when predicting Y, and it's in units of Y. It's not a percent. It's how much we usually miss Y by when we predict Y. Like on average, we usually miss by about this, and it's a plus or minus. So it's another uncertainty. It's saying if I make predictions, well, I'm usually off by about $60. And that is something we use for practical significance along with the R squared. Both of these measure of practical significance. And the R squared down here is also a measure of practical significance. P-values are statistical. R squared and RMSE are practical significance right here. You do want a small typical miss, and it's just right there. It's the residual standard error. It's just another name for it. So don't be confused on this, or I'll make it only show this. The residual standard error is the RMSE. And, that's R squared. So there's the RMSE, which is the residual standard error. Whenever you hear standard error, think of uncertainty. So this is uncertainty in the residuals. This is the uncertainty in your estimate of the slope. This is your uncertainty in the estimate of the intercept. So just different types of uncertainty. You're like, I think the intercept is this, but I could be off by about 9.4. I think the slope is this, but I could be off, or I think the slope is 1.76, but I could be off by about 0.42. When I make estimates, I'm usually off by about this amount. It's just uncertainty. It's just variation in the data. That's what standard error is. The measure of practical significance R squared is percent of variation in Y explained by the variation in X. We're messing up the numbers, but that's okay. So blank percent of the variation in Y. I only want the R squared on there. Go away. I'm going to break it. Sure. Blank percent of the variation in Y. So 10.36. Always multiply it by 100%. Of the variation in, and we're just going to say the Y variable, price, is explained by the variation in age, bids. And you could say, knowing the bids on an Xbox gets you about 10.36% of the way to understanding the variation in price. Another great way of saying it. That's perfect right there. The p-value of the regression? Well, we're just looking at the p-value of the slope. Which is... If you're not a fan of scientific notation like me, I like to see those zeros because I like to know how significant it is. P-value slope right there is going to tell us it's very, very, very statistically significant. And we have evidence that it reduces the sums of the squared error from the naive model, which is good. It means we don't think the slope is zero. A lot of things we talked about there. Yes. Last question. Let's go back to this. Last question time. How you doing, Max? Looking pretty good. Making sense. If you have questions, let me know. We'll be close to the true. We got 95% confidence intervals. Oh. Yeah, it's the end. Same thing we've been doing. End of your assignment, just like the end of the activity. Let's take a look. When you make confidence intervals, you could do it with the output by going plus or minus 2 standard errors. So making the confidence intervals, you would just take the estimate and go plus or minus 2 standard errors right there to make a 95% confidence interval. But there's a much quicker way by going to confident, and on confident, you can just run it and get your 95% confidence interval. You can make whatever percent confidence interval you want by going to level, and we won't do this, but we could put in like 0.80, and notice it goes from 10 to 90 because that's the middle 80%. So now we have an 80% confidence interval, but we don't want that. We want that 95, which is actually the default value it gives you. So we see that right there, and let's clear and only look at that. Now, here's the important thing. When we talk about this regression model right here, which let's go view it, not that one. I mean, it is, but let's view it a little bit only by itself. Viewing this regression model right here, we do not want to see that its slope is the same as the naive model. The naive model is a line that is equal to the mean of the y variable. Good practice to know that. And you can see the naive model behind me right here. So is our line different from the naive? Well, the naive model would have a slope of 0 because it's a flat line. Our line probably has a slope somewhere between 0.92, so it might be a little bit less than this, or it could be a little bit more. We estimated the slope to be, let's look at the estimate of it again. We estimated the slope to be 1.77. Now here's a trick though. We could actually show you the following output and ask you to get the estimate. So Max, 100-point question right here, Max, is a tough one. How could you find out what the slope was estimated to be? Ooh, I've put this question on the test and tricked a lot of good students with it. How could you find out what the slope was estimated to be? And think about what the interval does. Like think where my head's at. And if you have an interval estimating the slope, or interval telling you what the true slope might be, what was the slope used to estimate the slope, and what could you do with those numbers to find the value in your output right here, which was 1.76. How could you find that value of 1.76? Yep, just do that, average them out. Take the two values, add them up, and you got it. I have tricked very good students with that. And there's the value right here we see because it's at the center of the interval. Yeah, that's totally it. That's like, just think about it. I was like, okay, wait, it's at the middle of the interval. So let's just average those values. If you think about it conceptually, sometimes it makes sense. You don't want to memorize formulas. You don't want to be like, okay, wait, the formula for this is this. You just want to think conceptually through it. You can use AB line to amend the visualized model, or you can use AB line with plot. I think you can. You do that? I think you can. Ooh, let's take a look at that. Visualize model, M. AB line, horizontal, equals 100. Max, worth a button. I'm pressing all the buttons today. So we want to go here and go and do the following. Look at that, Max. Great answers, Max. It is using the plot window, so we can do it. We want to go to the mean of the Xbox with the price. And now we've got it at the mean. We want to increase the line width of it to something like 3, much better. We can go to, I can't remember line style. There's a line style. And then we want to go to col equals, we're going Rocky Top on this. We're going hashtag FF8200. There's some Rocky Top right there. And then we could probably add on our text and 6100. So 6100, comma, naive. And there's the naive, and then we need to add the col to this. Col equals, and do your code in little bits right here. I'll drop this in the chat here at the end. And look at that, Max. Excellent work, Max. A little bit of work. And we have it right there. Showing the naive model, showing our model on this plot right here. Where's line style? I can't can't remember the code for line style. Line style. There's a code. Here it is right here. LTY. I'm going to go LTY2. So we need to go to this right here and go LTY equals 2. There we go. That's got it. And here you are, Max, right here. There's our new plot. We just did all that code right there. And once again, do it in little bits right here, but that's in the chat right here for people to see it. But you can compare your model to the Naïve, and we actually just added it on. But good call there, Max. Why not try with the visualized model and just append code to it and just draw it on there? And I love doing this kind of stuff. I love that, you know, we can manipulate things if we get good and practice this. If you had asked me to do this years ago, would not have been happening. I'd have been like, oh, maybe, I don't know. And I'll still say it's a lot of questions. Some of my students, where can we find a video for visualization number 5? Great question, Callie, right there. Today we were doing it. Someone mentioned it in class today. Let's go check this out. Let's go find that real quick. I'll drop the link in the chat. There I am live right now. 3 people watching. Office hours. There's office hours today. When's that one coming second? Visualization number 5. Regression right here. We did it. That's the 27th. I think we did more in depth. 28th, I think in the morning we did more in depth. This is a review. Okay, wait, this is the review one. So I think this is the one where we did it more in depth. So if you see any of these that have visualization number 5 right here. Yep. Let me copy the time. You're welcome. So there's one of those right there. If you go to any of the videos, I mark them usually later at night. Hopefully, I usually get them done the same day. Sometimes a little tired. But does this make sense, Callie, right here? That you can go to any of these videos and you'll see what I'm covering on the videos. I have to come back and mark them later at night. And then also, we've got the playlist right here for the visualizations. But let me know if you have any questions. Email me if you're stuck. But we cover the visualization, how to do it, and we go over some interpretations right here. Yeah, and this is the first time we did it where we wrote out all the interpretations. If you're stuck on anything or have questions, let me know. And guess what we just did in this whole video? We just did a lot of regression. Awesome, Callie. Great work right there. That's got it. That's how we do regression. We're just doing a bunch of regression right here. Bunch of code, bunch of regression. Takes practice. With that, Puppet Shark, do you have a good day today? You going to have some fun on fall break, Puppet Shark? Yeah. We never see you anymore, Puppet Shark. You're not around as much. Even your little friend. Yeah. You're not around as much either. We will be back, though. Everyone, great work. I know these videos get watched a lot, and I'm really proud of that. So we will be back. I'll put on my 80s serious music. It is fall break. Everyone have a great fall break. We'll be back more. Email me those questions if you got it. I'm going to take a break, eat some dinner. I'll be back. Bye for now, everyone. Bye. Time for dinner. You're welcome, Max.